So this is systems of n particles, multi-particle system. This is in section 2.4 of Schaub and Junkins, and I will try to match their notation. This is going to be some theory. So what do we have? In this situation, we have, and I will get an image up here. So this is showing a bunch of particles. All these black dots are particles, and their location with respect to an inertial frame. So here's our, I like writing those in red. So this is our inertial frame, inertial origin. And we have a bunch of particles like this one, mi, and we will write their positions. So Ri, capital Ri, is the position of mass mi. And by that we mean, so from the inertial origin to mi. So it's the position of mass mi with respect to the origin O of some chosen inertial frame. And we might, just to remind ourselves, there's sort of a collection. I'm just putting this dashed line around it. So it's kind of like, we've got some particles. What do we have here? 20 or something. So there are many particles. And so the index I goes from 1, some particle is number 1, to particle n. And please don't get confused. I'll make this as a fancy looking n if you want. Here n is just the total number of particles. On each particle, there is a force. So on this particle mi, there is a total force. Maybe I'll write that in red just to be kind of weird. So Fi, this is the total force on particle I, or I mean mass m sub I. So that means Newton's law for particle I. The equation of motion is going to be F equals m, Fi equals mi, 2 inertial derivatives of r, so the acceleration. So in some sense, if these are n vector equations. So if we've got 3 dimensions to describe each particle, this is 3 times n second order ordinary differential equations for the position of this system of particles. But we're going to do something to help simplify this situation, because I haven't said, oh, what's this C and RC and all that? Well, we're going to first resolve the forces into something. So we'll decompose. Instead of just saying Fi is the total force, we will resolve it or decompose, whichever you prefer. We're going to resolve the total force into 2 different types of forces. There are external forces. So I'll write those as Fie. This is the external force on mi. And then there's Fij. This is internal force due to particle m sub j. So let me put in I'll label this one up here. Suppose this is mj. So the index j is going to go from 1 through n as well. This force Fij, so that means it's the force on particle I due to j. Okay. And so that means there's a force due to all of the other particles. The external forces are just whatever's left over. So forces that aren't due to other particles. There's only 2 types of forces in this setup. There's internal, so something that's due to another particle. Think of a bunch of point masses gravitationally attracted to each other. And then there may be an external force, which means a force due to something outside this dashed line. Some larger gravitational body. don't know. I like to think of a rubble pile, an asteroid rubble pile. And this is the interaction between each of the pieces of rubble. But then there's the force due to the sun, if you want. So there's the external force. So there's a force that's not due to another particle. So we call that the external force because it's often due to something external to this system. So now we will write particle, Fi, the total force on particle I, is equal to, we can keep these colors consistent, the external force plus sum over J goes from 1 to capital N. We don't include, there's no force of the particle on itself, so we exclude I. How did I do? That was in maroon. There we go. So we can resolve total force into external plus this sum of internal forces. And now we'll do something interesting. We want to know the total force on this system of particles. Total force on the entire system of particles. And I'll write that as F total to make it clear. So F total equals it's going to be the sum from 1 to capital N of the total force on the particles. And now we'll substitute in what I've got here for how I wrote how I decomposed or resolved the total force into external plus internal. So we'll get a sum from 1 to N of external forces. Plus, now we've got a double sum. I don't like double sums. Well, you'll like this one. So this is, I goes from 1 to N of J, and I'll just say from J not equal I to N of F I J. But now we use Newton's third law, which is that these forces between particles come in equal and opposite pairs, right? So the force on MJ due to I, F, J, I, right? F, J, I equals negative F, I, J. So in this double sum are embedded all of these pairs. So pairwise, all the internal forces cancel out. So this double sum goes to 0 since all internal forces cancel out. And we would say specifically they cancel out in this pair sort of way. So they all eliminate one another. And then what we're left with is this, the sum over the external forces. So we'll call that FEXT. So this is the total external force. So notice, what do we have here? If I drop this down over there, the total force on this system of particles is just the total external force. We're building up to something. And the next step of it is defining the center of mass for a system of particles. Right, the center of mass, this point C that's shown in this figure up here, that's you could think of it as the average location of the system. You've got to give an average location. It's like a mass-weighted average location of the system. So let's define that. Center of mass. Sometimes it's just abbreviated as c.o.m. Sometimes you don't even put the period. It's just c.o.m. And it's often written with this, bizarre looking symbol that they put on crash test dummies. So we'll define the center of mass. So the center of mass, that point C, right, this is RC. What's that going to be? It's going to be 1 over, and here, capital M is the total mass. Sum from 1 to capital N, MI, RI. Total mass, M equals sum from 1 to N, MI. All right. So I've, sketched one up here. There's where the center of mass is. And this is giving the position of the center of mass with respect to our arbitrarily, in some sense, arbitrarily chosen inertial origin. Why do I say arbitrarily chosen? Maybe there's nothing special about that point, but it's a reference point that we've chosen, at least to do some initial calculations. Maybe we'll pick another point later if it's convenient, but this is it. So the average location of this system of n particles is there. And later it'll have some physical interpretations, but right now it's just kind of an average location. You might say mass averaged, mass weighted average location of the system of n particles. We can now write Newton's equation of motion for the system if we want. Why are we doing this? Let's write Newton's second law summed over all the particles. There we go. So I'll write it this way, right? I wrote up there that each particle obeys Newton's law. Now I just flipped it. Mass times acceleration equals the total force on each particle. What if I just sum? I'm going to move this over so I can take a sum. So this is true for each particle. It's also true if I now sum over all of the particles. So sum from 1 to n. All righty. This right-hand side, right, the right-hand side here. Right-hand side, as we've shown, if you look up here, this highlighted part, it's equal to the total force, which is equal to just to the external force. Total external force on the system. What about the left-hand side? Well, if you look at this, how we've defined the center of mass here, this purple thing, take the sum. Well, we're just rewriting that. So the left-hand side, LHS, take the center of mass equation, take the center of mass definition, and just rewrite it. Move capital M to the other side. Now, take 2 inertial derivatives of each side. Take 2 inertial derivatives. We know what inertial derivatives mean. It means derivative with respect to that n frame. Take 2 inertial derivatives. We'll get, well, the mass isn't changing, so that nothing happens there. We get RC double dot equals sum. Each mass isn't changing. RI double dot. Oh, hey, what do you know? That is the left-hand side of the equation we care about over there. So this becomes MRC double dot equals FEXT, which is just a single vector ordinary differential equation. Right, it's got 3 components. It looks like Newton's law. It came from summing over Newton's law for each individual particle. But something weird happened. That weird thing is that all of the internal forces canceled out and we're left with just an external force over here, which is often easier to deal with. Or there might not be an external force. If there's no external force, then more magic happens. So how do we describe this? This is, if you want to follow along, this is equation 2.48 in the book. It calls this the Superparticle Theorem. What it means is that the center of mass, the average location of the system, moves as if it was a superparticle of mass m, the total mass of the system, under the influence of a force Fext, the total external force. So it looks like F equals ma, but it's got something, it arose because of the pairwise canceling out of internal forces. So it's called the Superparticle Theorem. The special case is if all forces are internal. That is, there's no external force. If there's no external force, and we're talking about no total external force, right? There could be on each individual particle an external force, but if somehow by some magic they cancel out, then you've got a total external force. So I should probably not say all forces are internal. I should say there's no total external force. Special case is there's no total external force. That implies that mRC double dot equals 0, which implies that the velocity, the inertial velocity of this collection of particles, the inertial velocity of the center of mass of the collection of particles is a constant. It moves with constant speed and constant direction forever and ever. It doesn't tell us what the rest of the particles are doing. They might, who knows? They might be doing some crazy stuff. So this means, if I were to sketch out what this means. So for this case, the center of mass moves with constant speed on a straight line. So if I've got my inertial frame, here is, let's say, the initial location of the center of mass, and it'll just be kind of moving the constant, the vector, constant speed and constant direction forever. So the initial, let's say, here's the initial location of this cloud of particles, and they've all got their own motions. I don't know what they're doing, something. At some later time, right, the center of mass has just sort of stayed moving on this straight line. The particles might have spread out. I don't know. Maybe they've spread out. But the center of mass is still doing its thing. And so what this means is that the motion of a multi-particle system can be decomposed into two types of motion, or resolved. Two types of motion. And those are motion of the center of mass. What I'm saying here is true independent of whether or not the total force, total external force is 0. So I've shown here on the left, this is the case of total external force is 0. This thing is moving on a straight line. But over here, you could always decompose the motion of the multi-particle system into motion of the center of mass and then motion of particles with respect to the center of mass. So we might call the motion of the center of mass would be the translational motion of the system. That just sort of says roughly, where's the average location of this system? The second one is the motion of particles relative to the center of mass. And this could be, it could be that the particles are spreading out. So there could be some expansion of, think of what the initial cloud of particles was. I don't know what I didn't use orange before, but it's kind of, maybe this part of this, the cloud of particles, if we want to call it that, is spreading out. Could be expansion. Maybe they could be swirling. These are not technical terms. This is just to kind of give you a visual. Rotating, maybe contraction is happening. Contraction. kind of moves like a very deformable body, although they're separate particles. Right, so we've got a cloud of particles. And I like to think of you might not know this, but many asteroids are actually rubble piles. So here is a rubble pile. I mean, some asteroids are actually solid masses, but many of them, and this came as a surprise to those who study this, many of them are like you hit them with your fist and they would move away from each other. So they might be just kind of loose collections of boulders. And so this is a nice visual of a collection of, if you think of them, all these boulders as point masses, well, the center of mass is moving in a pretty well-defined way through space. But, this rubble pile, maybe it's getting bigger, things are spreading out. So here's like one snapshot, and it's not necessarily moving on a straight line. This is moving around the sun. So this is the path of the rubble pile, if you want. It's also, a more engineering example would be a satellite explodes. And this is happening a lot because there's a lot of space debris. So satellite explodes, and now the thing is spreading out all over the place. Any of these pieces of debris, like one explosion can cause thousands of pieces of debris. And eventually they might hit George Clooney out in space or something. So this would be a case where the total external force is not equal to 0. Let me show a video. This is a simulation. I didn't do this. A collection of point masses. It's actually a simulation of 2 galaxies, and I think it's 2 galaxies. One's kind of spherical, the one on the bottom, and then the other one is ellipsoidal. Each galaxy is a collection of point particles, each star kind of moving around the center of the galaxy. So these are 2 things where you could see their center of mass, but they're going to collide and merge. It's not a rubble pile, but it's kind of cool. This isn't what our galaxy is going to do necessarily. I like to see all all those arms that get taken out. And astronomers have seen, you can look out in space and there are galaxies at various stages of collision. Like what we're showing here is taking place over billions of years. And not to concern you, but the Milky Way galaxy is on a collision course with the Andromeda galaxy, but it'll be billions of years before that happens. So I'm not too concerned about it. Yeah, when the Milky Way and Andromeda collide, I don't know what it will be called. I have no idea. There won't be anyone around it. Name it, maybe. We will have moved on, possibly. Well, once we find that wormhole near Jupiter, right, we can go anywhere. So that's a superparticle theorem. The upshot is this thing on the right about how the motion of a multi-particle system is decomposed in the motion of the center of mass and then the relative motion, which, like if you're a galaxy, there could be a lot of things going on. Once we restrict ourselves to the case of each of these particles, instead of moving independently, they're all rigidly attached to each other. Once they're rigidly attached, that's a rigid body. And the only type of relative motion, the motion of the particles relative to the center of mass, imagine like a crystal structure. And all it can do is rotate. The only type of relative motion allowed under the rigidity assumption is rotation. All these other things will not happen. You could, of course, relax rigidity and say, no, this moves more like Jello or some kind of flexible thing. And then you have a deformable body, but let's not deal with that. That's complicated. So we'll look at the most simple thing eventually. We're still talking about multi-particle systems, and we need to do a little bit more with the multi-particle system situation. Let's do it. Multi-particle systems, you can define the angular momentum and the linear momentum. and kinetic energy. I love those things. Kinetic energy, potential energy, linear and angular momentum. And the kinetic and the potential energy are useful because then you could do conservation of energy, which is pretty awesome. So the total kinetic energy, I'll just write it as KE, the total kinetic energy for the system of particles, sometimes that's just written as T. And so it'll be the sum from 1 to n of the kinetic energy on each individual particle. For each individual particle, this is 1/2 mi, the magnitude of the inertial velocity of each particle. So think of the diagram up above. Magnitude of the inertial velocity squared. So this total kinetic energy is just the sum of that. Sum from 1 to n, 1/2 mi, inertial velocity squared for each particle. The total potential energy depends on the forces at work. So the total potential energy, we usually just write that as V. And you might, can we write this as the sum of the individual potential energies? Yes. There's some complications sometimes though, because you might have two particles and the internal force between them is related to a potential energy. So I'm just going to leave it as that for now. And then we'll look at an example later where we can write that total potential energy. There's also the linear momentum. This total linear momentum for the system is, we'll just write that as P, and it's the sum, as you might guess, of the individual linear momenta, where, let me put over here, what's the individual linear momentum? MIRI dot, right? It's mass times inertial velocity. So if we add all of these up, what do we get? MIRI dot. If you compare with the formula for the center of mass, then this ends up being the center of mass equation. If you take just one inertial derivative of it, you would get that. So we move the capital M over here. So this comes from the definition of the center of mass. So we can just plug into here MRC dot. So the total linear momentum of the system, all of these formulas are true. This one might be the most useful. The total linear momentum of the system is equal to the total mass times the inertial velocity of the center of mass. And then if we were to take the time inertial derivative of that, so P dot, this equals MRC double dot. And we saw up above what that was from the Superparticle Theorem. This is the total external force. Some Superparticle Theorem. And this has implications. So if the total external force equals 0, then the total linear momentum is a constant, which then goes by the name conservation of linear momentum for a system of particles, which can be useful. So it means, let's say all you have is 2 particles, and you know what P1 is, right? Because this P over here is the sum of all of the P's. P1 plus P2 plus all the way to Pn. So that sum is constant. Even though each individual momentum might change, the sum of the momenta is constant. So we've got P1 and P2. So P1 at some time plus P2 at some time is always going to be what they were initially, if we call that time 0. And that can be useful. Here's for example, if the total linear momentum is 0 initially, then it is for all times. So P1 plus P2 equals 0, which means you automatically know that these have equal and opposite momentum, linear momentum. Anyway. Maybe we'll use that at some point. We could define the total angular momentum for a system. So remember, the angular momentum's weird in that you always have to define it with respect to some reference point. So if we use the inertial origin as a reference point, so let's say with respect to the inertial origin, O, this is going to be the sum of the individual angular momenta of each point. So I'll write this as I sub O. Hopefully that's not too terribly confusing. I-O just means the position, this was a capital R, position of each particle with respect to the inertial origin cross the mass times the inertial velocity, which we also called little pi. So there we go. You could also write this as Ri cross M Ri dot the inertial derivative. So that's that, if you want. This is just the sum from 1 to n of Ri cross M Ri dot. So that's the total angular momentum. The time derivative of the total angular momentum equals, oh no, I'm using L, capital L, L sub O. This is the total moment on the system. And what's that total moment? LO is the sum of the individual moments. So we'll just sort of write it this way. 1 to n Ri cross the total force. And so they're just like there's a conservation of linear momentum, there could be conservation of total angular momentum. If this equals 0, then the total angular momentum is a constant. And so that's called conservation of total angular momentum of the system. Okay.